Hi everyone. I really enjoyed Olympiad number 2 this year for the junior division. I thought it had some great problems. I hope you guys enjoyed doing it. There's only one problem that I was a little bit annoyed at, but that's okay. You'll see when we get there. And yeah, some very fun solutions, cool tricks. Didn't really have to use much brute force, maybe for the last one. Okay, enjoy the video, and I'll see you at the end. Bye. Oh, welcome to the first problem of the second Olympiad. This is exciting. The answer to this question, which was what you see here before you, is 1,000. And I don't know how you're feeling about that. Some people might be very happy to hear that. Others might go, oh, I just missed it. This is a great example, which, I talk about this all the time, but a great example of how you can get a solution using brute force, or you can go for an elegant solution where you found a pattern or maybe applied some knowledge that you had to a simpler problem and applied it to this one. The brute force technique for this one is very, very simple. Okay, clearly you would just multiply 28 times 7, right? You get some answer. Then you do, 28 times 3, get some answer, so on, and just add. We don't want to do that for a few reasons. One, it takes up a lot of time. And two, I don't think that we're really applying our brain the best when we're brute forcing these. We have to look for a pattern. And straight away, I saw something very interesting here. Here's what I saw. I noticed that 28 appears in this one and this one. And I noticed that 10 appears in this one and this one. And immediately in my mind, when I see something like that, in this form anyways, I think, distributive property of multiplication. Distributive property. Now, I've talked about distributive property a lot, so my 6s and 5s probably feel like, oh yeah, I think I remember that. My 4s, guys, probably not so much, but we have spoken about this before. So what is a distributive property? I'm going to break it down a little bit in some simpler steps, and then we'll show how we can apply it to this problem here. So give me 1 second. Okay, so the distributive property can really be best understood if we look at the geometry of what's going on here, because that's where it arises from, okay? It's not the other way around. It's not that the numbers have sort of dictated what's happening to the shapes and the geometry of the world. It's the other way around, right? The shapes and the geometry of the world have helped tell us how we use our numbers, okay? So here's a rectangle, right? Its area is 10 times 12. So I want to write out that equation, and I do so very simply. 10 times 12 equals 120. Okay, but now suppose I cut somewhere along the length of 12. So maybe I make a cut here, just to separate these two. I'm not removing anything, I'm just cutting, okay? And I have to label my new side lengths now. So perhaps I would say that this one is 3, and this is 9. All right, I don't know what that's doing. Okay, now how would I write this new equation for the area? Now the area is not changed, it still has to equal 120, but watch how I can write this. I can say that this area here is 10 times 3, 10 times 3, and then if I add to that, right, this area here, okay, then I'm doing 10 times 9. This equals, you guessed it, 120. So what have I done here? Well, check it out. What I've said is, as long as you have an equation in this form where you've got two things being multiplied plus two more things being multiplied, you need to think about this as areas of rectangles that you're summing together, and you could actually cut them any way you want. So 10 times 3 plus 10 times 9, I can actually regroup the 3 and the 9 to make 12 and rewrite this whole sentence as 10 times 12 equals 120. Very cool. Now, we've done a lot of this in the classroom, and I think me teaching you this here on Explain Everything on YouTube while you're sitting at home and your dog's barking and whatever, not the best learning environment, okay? But just know that there's a lot to this, and if you can understand the heart of, I think, that multiplication distributes, so distributive property, boy, you are really going to have your head around what's going to be happening to mathematics in the future, okay, especially as we get into deeper subjects. And it's just really nice for the elegance as well, just the beauty of it. Even if you're like, cool, I get it. There's a beauty here to how these things operate. So, oh, I'm at max zoom. Okay, so let's see, how do we use this to solve this problem? Well, I'm going to write it out again down here, okay? Hang on one second. Okay, so there are kind of two halves to this problem, okay, which I'll sort of separate here. Right? There's the left-hand side and the right-hand side of this sort of second addition symbol. So let's focus on the left-hand side first. We want to use our knowledge of the distributive property that we just showed you. Oh, hang on. Sorry, my dog walked in the room and was looking pensive. Okay, so here we are. We're going to use the knowledge of the distributive property that I just showed you to simplify this. Just in the same way we saw that if when I had an equation like, 10 times 3 plus 10 times 9, that was completely equivalent to 10 times 12. Okay, can you look at this equation up here in blue and see how that might apply? Hopefully you see it, or have an inkling anyways. Here it is. Look, the 7 and the 3. Those are the different parts of that equation. Therefore, the distributive property tells me that I can combine them, and I can say that this whole statement here is completely equivalent to 28 times 10. Now, where'd that 10 come from? Well, 7 plus 3 is 10. Well, 28 times 10 is trivial, 280. Whoa, that's pretty cool. Okay, let's go to the right-hand side of the equation. There we go. Now, don't be fooled, just because this looks a little bit different in that the similar parts of the sentence here on the right-hand side instead of the previous one on the left, okay, you can still apply these same rules because multiplication, it doesn't matter what order the terms are in. So I can actually say that this statement is completely equivalent to the sum of 31 and 41 times 10, or 72, right, the sum of 31 and 41 times 10, which is also trivial, right? That's just 720. And good old Olympiad, man, they love their numbers like 720 and all of these multiples of 60 and divisions of 360 and things. These numbers come up all the time. So the final step of this whole system is to simply sum these two together. So 720 plus 280, and I get, you guessed it, 1,000. Wow, how cool is that? I just think, what a great solution for a problem like this that originally, at first glance anyways, might seem quite challenging for brute force. Okay, let's go to number 2. Okay, I really liked this problem, and right below you here is actually the solution. This is the solution for how to get 19. So hopefully you wrote down in your answers, you wrote down something like times, minus, plus, divide. If you did this on a computer or iPad or something and you don't know how to do the division symbol, remember you can always look down for the question mark key, and right next to the question mark is the slash. Yep, and the slash is also means divide. Okay, so how do we solve a problem like this that is kind of takes a lot of creativity? Well, I hope some of you might have actually made little cards, and played around with this a little bit. What a great way to solve this problem. But there's a few things we can do to give us a leg up so that we're not just randomly sticking things in here trying to figure out, because that is not going to work. We're going to have to think about a few things. Okay, first off, we know that the answer has to be a whole number. Okay, and when I look at my operations of plus, times, and minus, by far the most the most pesky of these is, of course, the division. Okay, division is liable to get us into decimals if we're not careful with how we're using it. So let me give you an example. Oh, the other thing I want to mention before this, of course, but this really is a BODMAS problem, isn't it? Or if you're in North America, PEMDAS. And all that means is before you take into account a left to right approach of reading an equation, you must also take into account first certain types of operations. And in this case, we're concerned with times and divide. You must do those first. Yes, I know they should all be bracketed anyways, but who wants to deal with those kinds of things when you're trying to have fun doing a problem like this, right? Okay, enough on that. So let's deal with division first, because that could yield us some really crazy results that we don't want. For example, if I put division in the first place here, okay, so I have to do it first, and straight away I get 5 divided by 4. Oops, that's not going to give me anything close to a whole number. Well, I guess it's close to a whole number, but it's not. I could put it here, okay, 4 divided by 3. So then you think, well, maybe I'll put something else here and try to get this up to something divisible by 3. Oh, okay, look at that. That seems to work, but you don't have brackets, remember? You have to do 4 by 3 first. Okay, so that means maybe I put multiplication and you can do that one first. But no, 5 times 4 is 20 divided by 3. That's not a whole number. Okay, that's right. Well, only 2 places to go, boys and girls. So what if you put this one here? At first glance, it seems like that won't work, because no matter what you put here, you're still not going to get a whole number. But you could do 4 times 3 is 12 divided by 2 is 6. And if you went down this rabbit hole, you would have stopped very briefly. I think there's only 2 or 3 solutions you can get doing this, and none of them are 19. Okay, no matter what you put here or here like that, you're not going to get 19. Okay, so I'll get rid of that. That means the only place it can go is here. And I like this a lot. And hopefully you like this a lot too, because you would have noticed that 2 divided by 1 is just 2. So in essence, you've kind of removed the division from the problem, which is pretty great. Now you're left with some choices. And you could brute force this and just sort of put them in however you want, right? But let's use a little bit of logic for the final step here. You know you're trying to get up to the number 19. So you probably want an equation that is going to grow, is going to be big enough to get there. Why not take your 2 biggest digits, oops, and multiply them? Okay, so 5 times 4 is 20. That is awfully close to 19. Of course, if we add from here, we're getting away from our target, so subtract makes sense. That gets us down to 217. And then put this in here, the plus. And remember now, we have to skip and do the division first. So it's just 2. So we end up with, sorry, I feel like I'm not being very clear here. We end up with 5 times 4, which is 20. Okay, and then 2 divided by 1, which is just 2. So we get 20 minus 3, it's a wonky 3 plus 2, which in essence, if you think about that, is really just 20 minus 1, which equals 19. Yay! This is a cool problem. Very fun. Hope you guys enjoyed this one as much as I did. Okay, next one. All right, this is a very fun problem, and I'll give you the answer, and then we'll go over one possible solution. It's 4,042. That was the greatest possible centimeter length for perimeter from all the different shapes you could make, like from that area. Okay, so to solve this one, probably the best way to do it is make it, I would guess, make a table. And then maybe you can see some relationships between there. So I'm going to pause this. I'll draw up a table, and we'll talk about it. Okay, so I've drawn up a table to show widths and lengths of different rectangles I can make that have this area, as well as a section here to count off the perimeter. Now, I kind of locked into this one. I don't know about you, but if someone tells me, for example, what's a good example? Maybe someone says, okay, you've got an area of 60 meters squared. Okay, what kind of rectangles can you make? I don't know about you, but my brain always thinks about like the narrowest one possible, right? That is a 60 by 1. I don't know why, but to me, that seems like the first place my brain goes to is like, well, hey, that is a possible rectangle, right? You just said area. You didn't say you didn't care if it was very, very narrow, okay? Well, I did the same thing here. I looked at this question, hang on, switch my colors here, and I said, okay, an area of 2020, well, that means if you had a width of 1 centimeter, but you were like super long, 2,020 centimeters long. Okay, that is a fine area to have. What would your perimeter be? Well, let's remember the formula, okay, defining perimeter. Oh, it scale's weird. So remember the formula for finding perimeter, okay? It's 2L, okay, plus, I don't know why I'm drawing brackets here, but 2W equals P. Because you have two side lengths of both of these dimensions, right? Remember, perimeter is like all the way around. The fence around the garden. The fence around the garden in Minecraft, for those of you that like Minecraft. Okay. So double length. So I've got to double 2020. Well, that's easy. Okay, 4040 plus. And double width. Well, that's easy. Double 1 is 2. And then I add these together. I get 4,042. And I actually stopped there and said, oh, I think I've just got my answer. And yes, I do. I didn't have to go anywhere else. Okay? Because, I mean, clearly, let's say you go the next step down for width. Okay, so 2. That means you've had to cut this in half into 10, like that. Your perimeter is going to be much smaller, right? It's going to be 2,024, which is like almost half of what it was before. So this is absolutely the maximum perimeter you can make. To me, this is a pretty straightforward problem, and I think it was fun, and maybe the reading of it might be the trickiest part, actually, when I come to actually calculate it. Okay, let's go on to the next one. Okay, this was my least favorite problem on here, which is interesting because I usually really like problems that use combinatorics and you have to think about how things combine. I just find them so fascinating, especially when they have little subtle twists to them. But, okay, the answer for this one was 20. But the thing I found a little bit annoying about this is, I don't know, I wish they had come up with letters that could form better words than, air quotes, words, than or whatnot. And I know why they did it, because they wanted you to realize that to make different 5-letter words, the option of like swapping that E and that E, it's a valid option, but it doesn't actually change the word. It's still the word eerie. So I know why they wrote it this way, but I just found that to be a little, I don't know, a little lame, I suppose. These aren't real words, and I think this could have been a more interesting problem. Anyways, let's get to it. So, okay, so this problem sort of has two parts to it. There's kind of like a trivial part, I suppose, and then there's the tricky part, or like the twist, I guess. Okay, the trivial part is just up here at the beginning, okay? It says, how many words can be made by rearranging these 5 letters? Okay, so you've got 5 spaces, right? And for the first space, you have 5 choices of letters. 5 choices. E, E, R, I, or E. Great. Now, once you've used that, now you have 4 choices of letters. E, R, I, or E. Okay, cool. We're spelling the word eerie now, by the way. Okay, now for the third one, you've got 3 choices. Okay, R, I, or E. Now for the last one, you've only got I or E. Okay, this number that we've seen here, we've seen so many times. We've done this so much. Okay, this is a factorial, right? And we've actually memorized our factorials. We know that 5 factorial is 120. Okay, so that's the trivial part of this. Okay, just figuring out those combinations, okay, would have been a nice starting place to break into this problem. Okay, where's the tricky part come in? Okay, the tricky part comes into the fact that these 120 combinations include things like this. Let me zoom in a little bit here. Okay, it includes things like this spelling eerie, but it also means that it also includes things like, wait, why am I grabbing that one? Hang on. Okay, sorry, I had a problem with my layers here. I figured it out. Okay, so those 120 combinations I spoke about include this word here, eerie, right? However, it also includes this version of eerie. Well, it's the same word, but it's a different iteration. And our problem said, well, that's not allowed. We need unique words. It also includes this iteration of eerie. Ugh. Okay, so how do we figure this out? Well, we can cheat a little bit, because what we can do is we can actually label these E's so that we don't get confused. So we'll label this as E number 1, E number 2, and E number 3. Okay, so what are all the ways that these can be arranged, right? So that we get, oh, I wish that grouped. Dang it, hang on. I'm having problems. Okay, I can't forget about it, but we keep going. Okay, so what are all the ways that these could be arranged so that like E number 2 and E number 1 are differentiated from each other? Well, let's use our combinatorics knowledge again. Okay, we've got 3 spots that an E could go into for any given word, right? 3 spots. The first spot that E goes into, you have 3 choices, E number 1, E number 2, or E number 3. The second spot that E could go into, you have 2 choices. And the third spot, 1 choice. Oh my gosh, look at that. It's another factorial. 3 factorial is 6. So that means for any word we spell, be it eerie or re or ire, any word we spell, there are 6 ways to spell it using E's. So in other words, we've counted, I'll write this out because this is kind of the linchpin here. Okay, we've counted each word 6 times. Oops, so when we did our 120 calculation over here, we actually not double, triple, quadruple, quintuple, we sextuple counted our words. So we have to divide 120 by 6, and we get, of course, 20, our answer. Okay, so that is how I approached this one. Look, it's a fun problem, and I do really like the problem. I wish they had chosen letters or words that could, or they just gone with symbols then, you know? It bugs me that we're making fake words. I think that's a bit goofy. Anyways, on to the show. Wait, what? On to the next problem. Okay, this is a really cool problem. Anytime I see the word primes, I just get excited. The dice is shown twice here, and they show different faces. And I really like that they did this because this is a great clue for you. Right, because there's 6 faces on the die, and they've shown you all 6 primes. So you don't have to sit there and try to calculate the first 6 prime numbers or remember what they are. That's a big waste of time. You know, just look over here. They're right here. 2, 3, 5, 7, 11, 13. Okay, how do we solve this? Well, we're trying to figure out if we multiply these together and get some products, how many of them are going to have a 1 in the units digit? So it sort of makes sense that we have to kind of do all of the options. I don't really know of an elegant way to do this other than making a table. So let me draw up a table now and we'll fill it in. Hang on. Okay, I've really just drawn up a multiplication table, haven't I? Yeah. And across the, like for a better word, the x-axis here is the primes, and across the y-axis is also the primes, and we're going to multiply them because we're throwing 2 of these dice. Okay? All right, so I'm going to fill this table in, and we'll have a look. Hang on. I'm just going to pause here and show you. Look, filling in this table doesn't take as long as you might think, because once you complete one row, okay, one column, excuse me, you can also just complete one row, because they're the same. Okay, I can keep going. Hang on. Okay, here we go. It's all filled in. Okay, and now I can go on a hunt and try to find 1s in the units digit. Well, they kind of jump out, don't they? So 21, and oops, 21, and there we go, 121, then right next door. Yeah, that's pretty interesting, isn't it? So yeah, the answer was 5, by the way, to this problem. 5 over 36, right? Because there's 36 possibilities. Okay. Now, this is very intriguing for a couple reasons, and probably the most obviously intriguing aspect of this is that these are showing up on diagonals, right? And if you know anything about primes and prime spirals, you know, good old Ulam and his doodling, you know, discovered this whole series of structure within the primes that has been really studied to great lengths, and I just find endlessly fascinating. I love reading about these prime spirals and I guess the relationship the diagonals have to the prime numbers. It's very cool. I would love to continue this table, actually. I suspect there's probably more structure to this than what we're just seeing here. Anyways, cool. I think that's the last problem. Well, I always get excited on Olympiad Day. It's always lots and lots of fun. I was going to say something else. I can't remember. Oh, I would like to continue that table and see if I can find any other cool patterns, which I might do later. Okay, guys, if you have any questions, don't forget to contact me. See you later. Bye.